Welcome to Daikin web-based training. As you may know, recent air conditioners use new or alternative refrigerants in consideration of the Earth's environment. In conjunction with this trend, air conditioners that use new refrigerants come with a number of handling precautions, which have not conventionally been required. In this course, we will take up the current mainstay in new refrigerants, R410A, in order to learn about the properties of new refrigerants and key points for use. Let's go over what we will be learning. This course will allow you to learn through a comparison of the new refrigerant R410A and the conventional refrigerant R22. First, we will focus on the general properties of the refrigerants and key points for use. We will subsequently learn about the refrigerant oils used with each refrigerant and the key points associated with the change in the refrigerant oils. We will then go on to the key points related to high-pressure refrigerants. Last, we will cover the key points associated with the changes in the refrigerant component properties. We will go over the details of the above 4 items and the key points when working with new refrigerants one by one, focusing on the differences from conventional refrigerants. Let's take some time to learn about single and multi-component refrigerants. Single-component refrigerants refer to refrigerants that contain only one type of molecule. The conventional type of refrigerant, R22, an HCFC, is a single-component refrigerant. Some new HFC refrigerants that do not deplete the ozone layer, such as R32 and R125, are also single-component refrigerants. Meanwhile, a multi-component refrigerant refers to a refrigerant in which more than one single-component refrigerant is mixed to improve the performance of the refrigerant. R410A, for example, is a 50-50 mixture of R32 and R125 and does not deplete the ozone layer. The evaporation temperatures may differ depending on the particular refrigerants combined in a multi-component refrigerant. The number 4 in R410A indicates that the evaporation temperatures of the refrigerants combined within are different. In other words, R410A is a non-azeotropic refrigerant. Now, let's learn about non-azeotropic refrigerants. This diagram shows the saturation curves for R32 and R125 contained in R410A. The boiling points for R32 and R125 under standard atmospheric conditions are minus 61.1 degrees Fahrenheit and minus 54.6 degrees Fahrenheit, respectively. Liquid becomes gas inside air conditioner evaporators at a constant evaporation pressure. In the case of R410A, R32, which has a low boiling point and high cooling effect, evaporates first, and then R125 evaporates at a later time. As a result, the ratio of R125 within the R410A refrigerant increases as evaporation progresses, altering the composition of the R410A. We will now go over the precautions related to the differences in boiling points. Refrigerant is enclosed in a cylinder like the one shown on the slide, with the inside being filled with liquid and gas. Because R22 is, be it in its gas or liquid state, a single-component refrigerant, or 100% R22, there are no changes in composition, regardless of in what state the refrigerant is charged into an air conditioner. When R410A is charged into an air conditioner in its liquid state, there are no changes in composition. However, when it is charged in its gas state, it results in changes in the composition of both the refrigerant charged into the air conditioner and refrigerant left in the cylinder. Therefore, when charging a non-azeotropic refrigerant, be sure to always charge it in its liquid state. Let's learn about the precautions when measuring the refrigerant amount. When the refrigerant piping between the indoor and outdoor units of an air conditioner is longer than a certain length, an additional refrigerant charge becomes necessary. In doing so, it is essential to calculate the amount of refrigerant already charged in order to add the precise amount of refrigerant. The charging cylinder and digital scale are the devices used to measure the refrigerant amount. The charging cylinder conventionally used with R22 is prone to atmospheric emissions of refrigerant. It is now strictly prohibited to emit both R22 and R410A into the atmosphere, in consideration of protecting the Earth's environment. As such, charging cylinders can no longer be used. Please use a digital scale when measuring the refrigerant amount, regardless of whether it is R410A or R22. Let's now learn about the structure of the cylinder. This is a refrigerant cylinder for R22, and the internal structure is as shown here. This is a refrigerant cylinder for R410A, and the internal structure is also shown here. The R410A cylinder used in Japan comes in a different color to differentiate it from other refrigerants. It has a siphon tube and allows for easy liquid charging even when the cylinder is standing, and a sticker indicating that it is equipped with a siphon tube is attached to the cylinder. If there is no siphon tube, such as is the case with the R410A cylinders overseas, turn the cylinder upside down, face the charge port downward, and charge the refrigerant in its liquid state. Now, take a look at the refrigerant oils used for each refrigerant. Air conditioners use refrigerant oil in order to lubricate the built-in compressor components. The refrigerant oil for R22 is a mineral oil. Meanwhile, the oil used for R410A is chemically synthesized. Synthetic oil readily absorbs moisture and is more adversely affected than mineral oil when contaminated by dust or air. Therefore, the basic principles of refrigerant piping work, clean and dry, are even more important than they were conventionally. Let's now learn about what happens if you use the wrong refrigerant oil with a refrigerant. Minute amounts of refrigerant oil leave the compressor and circulate within the air conditioner. In order to circulate the oil along with the refrigerant in the refrigerant circuit and return it to the compressor, it must be soluble in the refrigerant. Mineral oil dissolves in R22 and there are no problems. But it does not dissolve well in R410A and becomes an impurity in the refrigerant. Synthetic oil dissolves well in R410A and must therefore always be used when R410A is involved. When R22 and synthetic oil are used together, the chlorine in the R22 degrades the synthetic oil, making it impure. Any impurities in the refrigerant circuit cause problems, such as capillary clogging, which increases the potential that the air conditioner will not be able to operate normally. Be careful to avoid using the wrong oil with a refrigerant. When working with R410A air conditioners, it is necessary to take special care during vacuum drying, pressure gauge installation, and piping work because of the high potential for moisture and mineral oil to get inside the air conditioner. Let's take some time to go over the key points related to these work processes. One of the basic principles in handling new refrigerants is the thorough implementation of clean, or in other words, the prevention of contamination by impurities such as mineral oil. Another is dry, which involves preventing synthetic oil that tends to absorb water from coming into contact with any moisture. Regarding clean, the gauge manifold and hose once used with R22 air conditioners cannot be used for R410A machines, because R22 machines use mineral oil. Use synthetic oil when applying oil to the flare piping connections for both the indoor and outdoor units. Since the vacuum pump uses mineral oil, use a pump that has a backflow preventer in order to prevent the backflow of mineral oil into the air conditioner. Regarding dry, complete evacuation is necessary to purge the air and moisture remaining in the connection pipes between the indoor and outdoor units from the refrigerant circuit. Now, how does mineral oil in the vacuum pump get inside the air conditioner? Let's learn about this point along with the way to prevent it from occurring. In order to conduct evacuation, first connect the vacuum pump as shown here. Next, turn on the vacuum pump. It starts purging the air. As the pressure reaches minus 14.5 pounds per square inch, the inside of the indoor unit and piping also gradually approaches a vacuum state. By maintaining this state for the prescribed time, the work is completed. If problems such as a power failure occur while the vacuum pump is on, shutting it down, the pressure of the pump inlet instantly returns to zero. However, the inside of the air conditioner and piping is still maintained at minus 7.3, causing air backflow. The mineral oil in the vacuum pump also backflows along with the air, inevitably getting into the piping and the inside of the air conditioner. In the case of a vacuum pump equipped with a backflow preventer, its built-in valve effectively prevents this backflow, even if the pump shuts down due to problems such as power failures during vacuum pump operation. Please note that even with conventional vacuum pumps, mineral oil backflow can be prevented by installing an external backflow preventer. Let's learn about how to maintain cleanliness inside the piping during brazing. As with R22, always replace the nitrogen when brazing the refrigerant piping in order to prevent any oxide film from forming. In addition, be sure to cool the brazed spots with a moist cloth before stopping the nitrogen. Let's now learn about the importance of nitrogen replacement. This is the piping before brazing. Brazing with a welding machine results in formation of an oxide film on the surface. If piping without nitrogen use during brazing is cut, you will see an oxide film also form on the inner surface. Meanwhile, if nitrogen is used during brazing, no film appears, and the inside of the piping stays clean. Refrigerant and refrigerant oil pass through the piping, and any oxide film on the inner surface of the piping will mix with the oil and degrade it. Therefore, be sure to perform nitrogen replacement when brazing, in order to prevent the degradation of the refrigerant oil. Let's now learn about the pressure differences between R22 and R410A, and precautions when handling them. In order to increase the capacity of air conditioners, refrigerants that reach a higher pressure than the conventional R22 are combined in R410A. As you can see on the saturation curve, at a temperature of 122 degrees Fahrenheit, the pressure of R410A is 435 pounds per square inch, which is 1.6 times higher than the 276 pounds per square inch for R22. Accordingly, the diameter of screws used on the maintenance port of air conditioners has been increased to 5/16 of an inch in order to prevent erroneous use of hoses and the like with a lower allowable working pressure. Be sure to use the respective gauge manifolds and hoses specific to R22 and R410A. Let's learn about the required strength of the piping that connects the indoor and outdoor units of R410A air conditioners. Since the design pressure for R410A is higher than that for R22, prepare copper pipes based on the design pressure of air conditioners to be used that meet the respective national specifications. Let's learn about the pipe connecting work, flaring and flare nuts, for R410A. The flare size, called dimension A, for R410A is larger than that for R22 due to the strength requirements. Be sure to use special tools for flaring. With regard to some flare nuts, the dimension B, or size of the flare nuts, for R410A is also larger than that for R22. Please use the correct nuts. The tightening torque is the same for R22 and R410A. Let's now learn about the air tightness test for the R410A piping. The piping air tightness test is conducted using different pressure levels in a three-step process. Please note that the pressure levels for the first and second steps are the same for both R22 and R410A. But the pressure level for the third step is higher for R410A. Finally, let's learn about the precautions related to the refrigerant component properties. As stated earlier, R22 contains chlorine, while R410A is a new refrigerant that does not contain chlorine. When conducting a refrigerant leak test, the electrical detection method is used for R22 in order to judge whether there is any leakage with a sensor that detects chlorine in the refrigerant. Meanwhile, the new refrigerant, R410A, does not contain chlorine, and the method conventionally used for R22 would not be able to detect any leakage. With the electrical detection method used for the new refrigerant, R410A, it is possible to judge whether there is any leakage with a sensor that detects hydrogen. This method can also be used for R22, because it contains hydrogen as well. Please make sure that the electric detector currently being used can detect hydrogen, and if not, consider replacing it with one that can detect hydrogen. The bubble detection method, with a soapy solution, is another method of detecting leakage, and it can be used for both R22 and R410A. This table summarizes what we have learned in this course. Let's have another look. R22 is a single component refrigerant, while R410A is a non-azeotropic mixed refrigerant. When working with R410A, you must always remember to charge it in its liquid state. Use a digital scale to measure the refrigerant amount, and check the structure of the cylinder. R22 uses mineral oil as refrigerant oil, and R410A uses synthetic oil. You must be sure to avoid erroneous combination of the oils and refrigerants. Use special tools for R410A air conditioners, and always use nitrogen when brazing. The pressure of R410A is 1.6 times that of R22. When working with R410A, use special tools and devices for R410A air conditioners, and be aware of the differences in pressure when conducting the air tightness test. With regard to component properties, R22 contains chlorine, which depletes the ozone layer. However, R410A does not contain chlorine. When conducting a leak test for R410A, be sure to use the hydrogen detection method that can detect the hydrogen contained in both R22 and R410A. Please always remember these instructions when working with new refrigerants.